Hey guys, welcome back. In this video, we're going to talk about vapor pressure and how it kind of works and how we kind of calculate it. So let's dive right in. First, with vapor, right? Vapor pressure, when you think about vapor, you're thinking about the gas phase. So right away, we want to talk about gas. We're thinking gas phase, right? So when you think of vapor, you think of gas and pressure, right? That's how we measure how much gas, right? Just when we talk about, mass, well, usually we measure solids in mass. We can measure liquids in mass, right? You can have a mass of water, but a lot of times we measure liquids with a volume, right? Okay. Gases are the same way. We can measure a volume of a gas. We can have a mass of the gas, but a lot of times we just measure the pressure of a gas, right? And so we talk about the gas, how much gas is in, right? How much of that liquid now is a gas, and the pressure is the amount. Now, when we talk about the solid or the liquid to gas transition, there's two words that come up sometimes. One is evaporation, and the other is vaporization. Is there a difference? Well, evaporation occurs at the liquid's surface. So this is at the surface of the liquid, and it's most importantly, it's not at the boiling point. So evaporation does not occur at the boiling point. It occurs at the surface of the liquid. All right. Vaporization, on the other hand, right, is the phase transition from liquid to gas. It includes boiling and evaporation. So a lot of times we'll use vaporization now as the overall encompassing liquid to gas phase change, if that makes sense. All right. And so if we had a container, there's my container, and I have in my container, we have the liquid. All right, we have a liquid, and there's these liquid particles. All right, we know that some of these are going to escape and become a gas. All right, okay, we know that, and we already learned that the intermolecular forces here are being pushed overall inward to the liquid, right? They're pulled in due to surface tension, right? So we know that the particles are pulled in due to the intermolecular forces, which we call surface tension. All right. So in those, and that water, in that liquid, and all those particles, right, they have a temperature. But let's dive into this. So in a sample of a liquid, and this, we're going to say this is open to air. That's important. So this is open right now. There's nothing there. There's no lid. All right? There is a distribution of molecular speeds And if the speeds are different, there's also different kinetic energies. And this is due to thermal energy. All right? Just like gases. All right? And so when you think about if you have a 18 milliliters of water, right? 18.02 milliliters of water at 4 degrees Celsius as an average, you have 6 times 10 to the 23rd water molecules. All right? And so if you have 180 milliliters of water, you have 6 times 10 to the 24th molecules. All right? And you can, 1.8 liters, you have 6 times 10 to the 25th molecules of water, right? These are astronomically large numbers, okay? And so when you talk about law of averages, like when you look at a road, for example, and you look at the cars, and maybe 50% of the cars are going the speed limit, so you got 5 going the speed limit, 1's going slower, 4 going faster, and when the 4 faster one's going really fast, right? But when you have, and that's just 10 cars that went by maybe on this little road. Here we have 6 times 10 to the however many, right? 23rd, 24th, 25th, 26 particles. Huge numbers of particles, right? Times 10 to the 23rd. Right, that's trillions of trillions. So there's a huge distribution of these temperatures. Not every particle has the exact same kinetic energy, right? Which is hard because the numbers are so big. It's hard to get our brain around it, right? It just is. Okay. All right, but because of this, some molecules move fast with higher or larger kinetic energy, some more slowly, with lower KE, right? But the average is the temperature, right? So we take the average and we get the temperature. Right? Some are a little higher, some are a little lower. Some are a lot higher and some are a lot lower. That's just how it works. You got a huge distribution of speeds. Right? Now, if the temperature is raised, all right, the average kinetic energy, all right, or the average thermal energy, is increased, and a greater fraction of molecules have enough energy to escape. All right? And that means to overcome the intermolecular forces, right, holding the liquid together. All right? So you need energy to escape, right? So you have the intermolecular forces are pulling the water, in this case, or whatever liquid you have, in, right? They're pulling it in. And then if the molecule has enough energy, like for example, a water molecule, it can leave, right? And when we add temperature to the sample of liquid, more of those water molecules can leave, right? And when we cool it down, less can leave. However, even if we kept, water at 1 degree Celsius, you put some water on the, get the porch wet, get the driveway wet, or sidewalk wet, road wet, that water will still evaporate, okay? Now at 40 degrees Celsius or 30 degrees Celsius, it's going to evaporate a lot faster, right? So if you get, where I live, summertime, that asphalt and concrete gets hot, hard to walk barefoot, all right? Put that water down, cool it off a little bit, right? But that water will evaporate pretty quickly in the sunshine, right, because of the temperature. In the wintertime, if it's cold and dark, you wet the concrete, right, it still will evaporate, it just more slowly. All right, so if we look at this mathematically, right, I have it that and this, so x and y here. All right. If x is my kinetic energy and y is my fraction, all right, how many particles? So if I'm cold at low temperature, all right, so at low temperature, there's not, let's just say we're up here like this, and then we're going to come down. Well, that's not the best. Let's try that again. There we go. Excellent. All right. And let's just say this right here, right there, that is the kinetic energy needed to escape. Let's just say that's what it is. I need that. So that means right here, this little bit can go. And again, my curve is not the best, but all right. If we raise the temperature up, all right, so we're going to do this T1, which is low. If we raise the temperature up, all right, we'll get a different distribution of speeds, all right, with a bigger fraction, right, that can escape, all right? It's a bigger fraction, all right? And so the area, so this is a curve here, so to speak, right? That's the blue curve. The area underneath the blue curve represents all the molecules, okay? And the area over here, and the blue curve, is how much can escape. The area underneath the purple curve, the cooler one, the low temperature one, right? All that area is the total amount, all right? And so the area under the purple curve should be the same as the area underneath the blue curve. I just shifted it, right? So I have the same number of particles, I just gave it, the whole sample, more energy. So we go from T1 to T2, right? So that means instead of having a more narrow, when it's colder, it has a more narrow, like, more narrow. As I get even colder, I can get even more narrow, right? But the area underneath the curve remains the same. So if it's colder, it'd be higher, right? And as we get warmer and warmer, this happens, and this happens, and this happens, if that makes sense, all right? And so that's kind of what's going on. And so to escape, right, right, a molecule must have enough energy to overcome the intermolecular force attraction. All right. Now, we can accelerate this, right? We know, go back to water. We can accelerate how much particles leave, right? You've all done this before. Hopefully you're allowed to use the stovetop. You've all put water on the stove, and you all put heat, right, in the pan, or water in the pan, put the pan on the burner, turn the burner on, and put heat to the water, right? And as you heat the water, it's going to start steaming more, and water is going to escape until it gets to the boiling point, right? Right? So you're adding heat, right? And you guys know the heat, we've talked about this before, but the heat required to vaporize 1 mole of liquid is called the molar heat of vaporization. It is always endothermic or positive. All right. So for example, H2O liquid going to H2O gas, delta HV, or VAP, right, is equal to positive 40.7 kilojoules per per mole. So that's what it takes to vaporize water, 40.7 kilojoules for every 1 mole. All right. Okay. So now, when we go into this, we now know we can vaporize water and why it's going to happen, right? How it's going to happen. We give it energy and it can overcome the intermolecular forces. Now let's talk about how much vaporizes. So now we're going to go to a closed container. All right? We're going to go, we're going to do vapor pressure. And so when we talk about vapor pressure, all right, I had that container here. All right, so we have our container. Let's not have a hole in our container. All right, and now we're going to put, I don't know why that came in narrow. Sorry about that. Okay, we're going to put a lid on our container. So now we have a lid. So we still have our water in here, H2O or other liquid. So we're just going to not have to be liquid. It can be any particles of liquid in here. All right, we got our liquid particles, and some of them are going to become gases. All right, our gas particles. Okay, we know we got the vapor up here, and we got the liquid down here. And the liquid can come, the gas can come down into liquid, and the liquid can go up into vapor. All right? Hopefully that makes sense. All right? So just like if you have a water bottle, if you leave it open, it can evaporate. However, if you close it and it's sealed, for the most part, it's not going to evaporate into dryness. All right? So in a closed container, which is different than the one above, where we did an open container. Now we have a closed container. All right. When the rate of evaporation or vaporization is equal to the rate of condensation, right? And condensation is what? Is when a gas goes to the liquid. And evaporation is when a liquid goes to the gas. Right? So those are our phase changes, right? So when those rates are the same, then the system, right? So this is a system. So this is a system. It is a system right now of just water, with water that's a liquid and water that's a gas. That's it, all right? So that's how we define that system. Systems can be big, small, complex, simple, right? That's a system. And so when the rate of these coming up, how many come up per time, is the same as how many of these come down per time, right? So the condensation is the same rate as the vaporization or evaporation, right? The system is in this new word, equilibrium. All right? So then the rates are the same. The rate of condensation equals the rate of evaporation. Okay, so the rates are the same. All right. So at equilibrium, all right, the partial pressure of the vapor in the gas phase is called the equilibrium vapor pressure. Right, at that temperature. So that's what it's called. It's the vapor pressure at that temperature. Right, because as we know, as we change the temperature, we're changing how fast the water's going to evaporate, right, until it boils. Okay, so vapor pressure, right, which would mean, right, that's the pressure up here. Put a big old P. Right, that's how much is up there. How much gas is up here. That's the vapor pressure, right? So now we can increase it. The vapor pressure which a lot of times we call it PVAP, will increase as the temperature is increased. Okay? Now, what's kind of fun is the boiling point is reached. Okay? When the vapor pressure equals the atmospheric pressure. All right? So when we can keep heating your water on your stovetop. So if you go back to your stovetop, you're heating your water, you're heating it, and then it starts boiling, all right? Well, that's when the amount of, right, the vapor pressure above the liquid is the same as the atmospheric pressure, okay? Normal, just so you know, normal, that word. Normal boiling point is at 1 atmosphere. Now, we might not be at normal, right? You go to the mountains, you're not at normal. Sometimes you're higher, sometimes you're lower, okay? So now, there is a relationship between vapor pressure and temperature. Because we kind of know that already, but there's actually a quantifiable way, all right? So when we talk about things, we like to get things in lines. So sometimes they're not in line, so we got to do lines. All right. First one, this one is natural log of the pressure, the vapor pressure, is equal to negative delta H over R, right, the heat of vaporization over R, times 1 over T plus C. So now that's a Y equals mx plus V format, right, where T is the X, right? So we're seeing how vapor pressure depends on temperature, okay? Now, so this is the Clapeyron equation. Oh, how do you spell it? Hopefully I said their names right. Okay. It's an exponential relationship, as you can see. What does that mean? That means as temperature increases, the vapor pressure greatly decreases or increases, right? So, right, an exponential increase, right? If you had oh, no, we don't do that. If we had, you know, x and or y and x, you know, it goes, that's exponential, right? So it doesn't look like there's much going on down here, but by the time you're up here, it's way up there. So that's an exponential increase. So that's what we're talking about. Now, there is something, we're going to do a lot of the 2-point form. Right? Because this constant, that's a y-intercept, c, b, beta, whatever you look at, right? Because this is y equals m, x, and b, right? Well, b is the y-intercept's the y-intercept, so we can have two lines equal to each other. You can derive this, but most of my students don't like to do that anymore. So natural log, right? And our book, current book, is it's p over p, right? Well, one of them is p1, one of them is p2. It doesn't matter which one's p1 or p2. Equals delta h over r and then we have the two temperatures, T and T. Now, this one, in the way we're doing it, is T2. That one is T1. And the temperature has to be in Kelvin. All right. These are in, the units for P have to be P1 equals P2. So it doesn't matter what they are, they just have to be the same units. What's R? 8.3145 joules per Kelvin mole. And delta H is typically in kilojoules per mole. So notice you got kilojoules here and joules there. Notice that. Okay, that's going to be a thing. All right. And so that would be your Clausius-Clapeyron equation. All right. For vapor pressure. So that's going to end vapor pressure. I hope that works. If you have any questions, let me know. We'll see you next time, guys. Bye.